Any sufficiently advanced technology is indistinguishable from magic.
Hello, I'm Professor Brian Keating, Chancellor's Distinguished Professor of Physics at the University of California, San Diego, and the co-director of the Arthur C. Clarke Center for Human Imagination. And today's topic continues this grand tradition of trying to understand how did we get here. Not only us, but also all these little twinkling lights in the background behind me in the Hubble Ultra Deep Field. Each image there, each pixel, each speck of light is a galaxy, not a star. And each galaxy there is comprised of maybe perhaps 100 billion to 500 billion stars. Perhaps they have planets, perhaps they have cosmologists, and perhaps they have curious characters like you and me. Because my motto is ABC, always be curious. And this is part of my outreach attempt to give information to you, the tax-paying public, and the communication of the most fascinating topics in all of physics and cosmology. And there's really nothing bigger than the question of how did the universe begin? And in so doing, we will take a journey back to perhaps the origin of time itself in the theory known as cosmic inflation. Now this is controversial, and this came about as a response to an earlier theory, which itself was first thought to be outlandish, and that was the Big Bang model. The Big Bang model was really first encountered as a consequence of Einstein's theory of general relativity. And that theory of relativity had within it the seeds of an expanding universe. And that expanding universe, if run backwards, would then predict that things in the universe, such as galaxies and maybe even other objects, would be compressed, perhaps, into what was called a primeval atom by Georges Lemaitre, famous Belgian Catholic priest. Inflation, the theory, arose, as we discussed in a previous video, as a response to the known flaws or gaps or holes in the Big Bang model that I call cracks in the cosmic egg. And those are going to be very briefly indicated and glossed over here. And I refer you to this video up here, where we talk about the problems in the Big Bang that ushered in the concept of inflation. Now, those three main pillars that cosmologists often talk about were flaws in the Big Bang model are also shown behind me in this video, but we're not going to talk about them again. I refer you to the previous video. The primary one that first attracted some large measure of attention is the so-called flatness problem. Why do all triangles in the universe, no matter how big or small, sum to an interior angle of 180 degrees? No matter how big you make a triangle out of stars, out of galaxies, out of even fluctuations in the cosmic microwave background. This was a puzzle, and the puzzle gets even more pronounced and more difficult and more vexing the earlier in time you go back. So starting from today, we know the universe is flat to a precision of about 1/2 of 1%. Meaning that there is no discernible curvature, positive or negative, positive being a sphere, negative being a saddle or Pringle. And the problem gets worse if you go earlier in time. In fact, it can get exponentially worse. It can get as bad as you want when you go back to the so-called radiation-dominated epoch of the early universe. So when the first elements were formed, they were formed during a period of time in which the dominant contributor to the universe's energy budget was in the form of heat. That would later become the cosmic microwave background radiation, but for that period of time was really just gamma rays and very high energy ultraviolet rays, and they were bombarding and dissociating and even causing atoms themselves and nuclei of atoms to dissociate if you go earlier back in time. So this is a great problem. Why is the universe so flat? And it must have been born, since the universe has to only diverge very, very slowly with time. As time increases, its curvature increases ever so slowly, then that means that in the early universe, it must have been radically more flat, if you can imagine it. Flatter than Florida, as I like to say. So when you look back into the early universe, it makes things worse. And so that was a problem in the Big Bang, because the Big Bang purports to explain the universe at its earliest moment, maybe even time equals 0. We'll explore the notion of time in a later video. So that was one of the gaps in the Big Bang model that led to the notion of the solution being needed, crying out for an explanation, not by fiat, not by God, because cosmologists find that notion antithetical to the practice of science, but instead to some kind of purported earlier, more primal mechanism. That will turn out to be inflation, spoiler alert. Now, the horizon problem is the observation that no matter which two directions you look in the cosmos, even if you look 180 degrees apart, looking in front of myself, looking all the way to the back, the temperature of the CMB is equal to a part in about 10 to the minus 4. So 1 part in 10,000 fluctuation will be the amount of fine-tuning of the universe's temperature. And this is thought to be impossible in any other cosmological scenario where you just propagate the Big Bang model forward from the earliest epoch in which we understand how the universe physical functions were taking place, namely the formation of the first light nuclei and their isotopes. But instead, if you go back earlier in time, the coincidence that's required has to be absurd. We have to have a fine-tuning and a degree of matching at the parts per 100,000 or even more if you go back to the earliest moments in the universe. That is known as the horizon problem, the uniformity, nearly so, of the cosmic microwave background's temperature. Historically, the first problem that Alan Guth was led to think about a notion of astroparticle cosmology involved what's known as the monopole problem, which is that if you extrapolate back in time, you go up in temperature. And if you go back to when the CMB was formed, it was formed at a temperature, characteristic temperature of the entire universe. If you had a thermometer, it would be about 3,000 Kelvin, and therefore it's cooled off by 1,000 times. The universe has expanded the scale factor by 1,000 times in those remaining 14 billion years nearly. But before that, you go back in time and the temperature rises again exponentially, and it goes as a very steep power of the size of the universe. In fact, if you try to make it zero, the universe would have infinite temperature, and those are problems in so-called singularity theorems that we're going to explore, in particular the Borde-Guth-Vilenkin theorem, which I want to get into in a future video. But before we get there, we have to understand why cosmologists like to talk about inflation so much, and we've gone a deep dive into some of the problems with inflation, but it's important to get a good foundation as to what inflation actually predicts, what it explains, and what it fails to explain, and what other gaps it has. And always remember, in science, the job of a scientist is not to explain everything perfectly with no uncertainty. It's to characterize the uncertainty that we have about the quantities we claim to know about. So no scientist should ever say we know something with absolute scientific certainty. There always has to be some uncertainty. In fact, it's not known that the universe is completely flat because we have this 0.5% uncertainty in its curvature. And that's astounding because when I was a graduate student, we thought the universe was essentially an open universe, which meant that it had about 30%, not 0.5%. It was off by factors of 60 or maybe 70% from what we know it to be today. So factors of hundreds, maybe even thousands of improvement just in 25 or 30 years since I was a wee lad and student at Brown University. Now, looking back in time, we look back in temperature. Temperature goes up, gets higher. Particle physicists think that we will unify the fundamental forces of nature that are at least the three most powerful forces, short-range forces, the grand unified theory, so to speak, contains within it the hopes to unify the strong interaction of nuclear physics, the weak nuclear force, along with electromagnetism. And electromagnetism and the weak theory have been unified, as we talked about earlier. In those processes of transitioning from one phase of the universe when it was dominated by perhaps two forces, gravity and a grand unified theory, or maybe even earlier going back to a theory of everything, and there's only one force, later on shattering, if you will, into four different manifestations, gravity and the two nuclear forces plus electromagnetism. When the universe underwent a so-called phase transition, it is thought that there could be leftover relics, sometimes called topological defects, one of which being magnetic monopoles. So as I explained earlier, magnetic fields, magnetic objects, if you look at a magnet itself, it always has a north pole and a south pole. Even when you crack it apart and you get a north and south and a north and a south, you never get an isolated north pole with no south pole and a south pole with a north pole. So the expectation was if the universe had a grand unified epoch, it would have transitioned through a phase transition that would have then led it to acquire within it these topological defects, of which one would be a magnetic monopole. And yet we've never observed a magnetic monopole. And there should be trillions and trillions and trillions of them, as we talked about and actually estimated in previous videos. And so it's actually quite astounding that we don't see a lot of these, and in fact that we even exist, because these monopoles would be quite massive, far more massive than the amount of ordinary matter in the universe, and that would cause the universe to collapse long ago. So our existence means that we might owe ourselves to the absence of magnetic monopoles, and yet in our best theory of cosmoparticle physics, they should be abundant. The universe should be rotten with magnetic monopoles. We believe that they're not because some process has diluted them so much that we don't see them today. And that will actually be culmination of what we talk about today. Inflation is a proposed solution to all three of these problems, and perhaps more. What inflation does is add to the early universe's Big Bang an even bigger bang at an even earlier epoch, namely not at the beginning of time, but perhaps as early as 10 to the minus 36 seconds after the origin of our observable universe, whatever that means, we'll have to get into in a separate topic. The universe underwent a hyperactive expansion. And in fact, that expansion wasn't constant, like stepping on the gas pedal with constant pressure. It was actually flooring the gas pedal and accelerating, increasing our velocity, or the universe's velocity, increasing the scale factor of space-time, which is described in a dynamical equation shown at the top called the acceleration equation. The acceleration equation shows that for any substance that has what is called a negative equation of state, in other words, most materials, like a gas in a piston, when you compress it, the piston wants to repel and go back out and be pushed out by the compression of ordinary matter inside of the cylinder. Now, if the cylinder were containing this material that had a bizarre property that the more you pressed it, the more it sucked in the piston inside the cylinder, that would be said to have a negative equation of state. And we don't know and encounter in ordinary physics and ordinary experience something with negative energy, but it is believed that the large-scale acceleration of the universe that we observe in distant galaxies today owes itself to a type of material and property of space called dark energy that has a negative equation of state parameter. This parameter W is believed to be sufficiently negative to cause late time, i.e. at 14 billion years after the Big Bang, expansion at an accelerated rate. But it actually doesn't need to be as big as it is to cause this property of space to expand so rapidly. Now, during this early period, the equation of state had this form. And as the universe evolves, the expansion of the scale factor, this quantity A, this is the master governing parameter of the universe. It's a characteristic scale size of our universe at any given moment, and it depends on the composition of the universe. We can't actually observe the scale factor A itself. We can only observe ratios of it and derivatives of it during inflation. The first derivative of the scale factor, namely how fast is the universe's size scale increasing or decreasing, it was getting bigger. And it was getting bigger at a rate shown on the left, just to the left of the first right pointing arrow. And that shows that as long as it had a value of that second derivative, as long as that value is greater than 0, the universe will expand at an accelerating rate. Later, when we plug in that equation and solve that equation for the governing equation of cosmology called the Friedmann equations, which themselves come from the Einstein's theory of general relativity in an expanding space-time, the amount of expansion, i.e. the Hubble constant, is very simple to calculate. The Hubble constant is the evaluation of the Hubble parameter, which is just the time derivative of the scale factor at any given moment. From the Friedmann equation, we get that the expansion of the scale factor, A of t, will grow exponentially at a rate governed by this Hubble parameter, hi, during inflation. Now, if this is constant during inflation, if h is constant, the universe will expand at a rate of e to the lambda over 3 to the square root power. So we can solve those equations. Those aren't actually very difficult to solve, and we can evaluate 3 different epochs. We can evaluate an epoch before inflation took place. I told you that inflation took place at a time we call a trillionth of a trillionth of a trillionth of a second. A second after what? Well, that we have to determine. That could be a previous universe's collapse. It could be the origin of time itself. That is yet unknown and very interesting to consider, and we will do so at length on this channel. But suppose there was this exponential period that then began at this trillionth of a trillionth of a trillionth of a second. Before that, the universe was just growing due to the fact that it contained a lot of heat. So somehow the universe was created or born or nucleated in an initial state before inflation in this paradigm that had copious amounts of radiation because of its small size and high density. Nothing material could really exist without getting completely annihilated and converted via E equals mc squared into pure energy. We talk about energy, we really mean photonic energy. Therefore, the early universe, the predecessor universe to inflation, that epoch, was radiation dominated. We know very well how the universe grows during radiation domination. And that will also take place after inflation ends. At this time, we mark T final. And as long as the universe grows during this period of time, it will have to grow exponentially fast at an accelerating rate. And that accelerating rate is governed by the value of lambda, where lambda here means the inflaton energy. And so when you design a model of inflation, you sometimes will work backwards from the observables. The universe is flat, it has no monopoles, it has the horizon problem, and we want to extrapolate a solution to it. We'll say, well, how much expansion did the universe have to have? That will set limits on how much the inflationary parameters changed or were their values at the early universe's first epoch. It's a simple matter to calculate to determine and to define what's called the number of E-foldings. That's the number of times the universe not doubled in size, but increased by 2.78. That number to the power n is typically what we call the number of E-foldings. And you can relate that, it's almost the square root of the number of 10x multiples of the universe. So how much does the universe grow in size as ordinary exponential notation? So, as I say at the bottom, if the universe was in this inflationary epoch for long enough, where long enough only has to be a trillionth of a trillionth of a trillionth of a second or so, we'll talk about that, then the universe can grow by a huge amount. So there can be an incredible growth in the scale factor of the universe, meaning that things that have the size scale of a proton can grow, if this number is big enough, to arbitrary sizes. They can get as large as a meter. So they can grow by tens of orders of magnitude from the early universe's inflationary epoch. And this is not proving that inflation took place by any means. It's just saying if the universe had a period of early acceleration, what would the consequences be? And how much does that acceleration have to do to the size of the universe? How much accelerate? How long are you holding down the gas pedal for? So we typically pick the time at which the unification of the strong, weak, and electromagnetic forces could take place. That equates to an energy. We can equate that energy, the energy of grand unification from 2 or 3 slides ago. We can convert that to a time. That's where we get this 10 to the minus 36 seconds, or a trillionth of a trillionth of a trillionth of a second. So we're really going backwards. So you don't even have to ask what happened after what. What was t equals 0 on this exponential notation where inflation begins at 10 to the minus 36 seconds. You can start from today and go all the way backwards to 14 billion years minus 3 minutes minus 10 to the minus 36 seconds, something like that. To produce the exponential expansion at that time, at 10 to the minus 36 seconds, requires that lambda be almost over 100 orders of magnitude greater than we observe the dark energy to be today. In other words, today we are witnessing an acceleration of A. The scale factor is getting bigger, the Hubble constant is increasing with time, and therefore we are undergoing a period of expansion via this dark energy type of phenomena, of which we don't really understand that much, and we will talk a lot about that. And we will ask the question, though, in this context, how big does the universe is dark energy, how big would it have to be back in the early time to account for the inflation that we believe is necessary to explain these lacunae in the Big Bang? And that's a huge differential. It's 107 orders of magnitude difference. So the curvature diverges and grows exponentially or geometrically bigger as you go back in time during this early epoch, during the radiation-dominated phase. In fact, it grows as the speed of light squared, which has dimensions of velocity, over something that has dimensions of velocity per unit distance per unit time, and that's the Hubble parameter, h of t, and also this characteristic scale r0, where r0 is the radius of curvature of a curved universe. Now we only know the absolute value of this term, or we can only calculate this from our Friedmann equations, but if you go back, and you go back early in time, you find that the universe is incredibly flat, and it gets flatter and flatter the earlier you go back in time. And in fact, you need a certain number of E-foldings so that the deviation from 1 minus omega, which governs how curved the universe is, becomes as close as you want to 0. In other words, we can make the universe born with a decimal place in its curvature and an infinite number of zeros if we want, and then finally a 1 at the very end. You can never make it perfectly flat by extrapolating from what today's values are if it diverges, but you can get it arbitrarily close to 0 curvature, which means that you solve today's curvature problem by virtue of the fact that in the initial moments of cosmic history, the curvature of the universe was so flat, so iron taught that the universe would have had so little curvature then that no matter how much it grew, you're basically multiplying 0 by a large number in the elapsed amount of time that the universe has had to grow. You're multiplying it by a decently large number, but you're multiplying basically 0. And you can get it as close to 0 as you want, such that by today you can get at most a 0.5% deviation from perfect flatness. And that is the only amount that is tolerable. So the question is, how many E-foldings do you need to get this flatness problem out of our hair? And that actually turns out to be a number that's not actually that big. It's 60 times. The universe has to not double in size, but increase by a power of e to some power, e to the 60th power, which is something like 10 to the 30th power. So it's a big number. It's a lot of foldings, but you're going from the size scale of a proton to something macroscopic, human scale, meter scale. And you're doing that, though, in an incredibly short period of time, 10 to the minus 36 seconds. And in so doing, you can make the universe completely flat back then, such that by now, even with a tiny bit of amplification of almost 0, you still have effectively 0 curvature. That's how inflation would solve the flatness problem. And it only needs to increase by this much to match observed data from the cosmic microwave background, as we've discussed in the previous video. The next problem is the horizon problem. We talked about that as a problem that really is indicative of the fact that the universe has a certain size scale over which it can communicate, and that's effectively the maximum distance that information can travel is essentially the age of the universe at any given moment times the speed of light. And it can do so in both directions, forward and backwards, left and right, up and down. And so the question of why is the universe so connected together today, 13 billion years later, more than almost 14 billion years later, can be solved by inflation by looking at how small the universe was at that time, the universe that would grow into our observable universe, how close was it to being completely uniform or very close to uniform at the early epoch known as inflation. So to do that, we talk about solving the horizon problem. The horizon problem is a description of how much the universe can vary from point to point, and how big the universe can grow within the bounds of the period of time known as inflation. So from the previous slide, in order to understand how much the universe has increased from the time of 10 to the minus 36 seconds, how big did the universe increase by? It went from a size of 10 to the minus 28 meters, as I said, much, much smaller than the size of a proton. And it expanded by 60 E-foldings, maybe for sake of making a convenient argument. We expanded from that size scale up by e to the 60th or e to the 65 for this comparison. So it went from the size of a subatomic particle, smaller than, say, the radius, classical radius of the electron, and it increased to the size of a whale. So how does this solve the horizon problem? After inflation, as we said, before inflation and after inflation, the universe is so-called radiation dominated. Its expansion rate, its acceleration, everything depends only on the amount of heat that's in the universe, not any matter. It's way too early for matter, like even quarks and so forth, to form. So the only substance that's there are photons. Photons are particles of light and heat. So the universe grows by this certain amount after inflation. It also grows at the same rate before inflation. And so this diagram is showing how big is the horizon. Over what distance could information be allowed to propagate, and tell different regions of the universe to set your thermostat to my value of the thermostat so that we come to equilibrium when 13 billion years plus elapse. Later on, we can show that the fluctuations in the amount of heat energy in this early universe were as uniform as required to solve the horizon problem. And you go through the calculation, and you find that at the time the universe produced the cosmic background radiation, this pattern from the WMAP experiment, that the universe has increased from the scale factor of 10 to the minus 27, and it's grown to a size of 10 to the minus 4, 10 to the minus 3 by the time the CMB was produced that we observed later. So we're really measuring how bad the horizon problem was when the universe produced the cosmic microwave background anisotropy. So we find that if the universe underwent this rapid period of acceleration during this very brief epoch, it only lasts, as shown here, for a very small fraction, 10 to the minus 35 of a second, 10 to the minus 36 of a second, very, very brief amount of time. And yet, in so doing, it can then terminate the inflationary epoch and end, and then the universe can evolve just the way we observed it evolving during the formation of the elements, and then after in matter domination, and now in lambda domination. And it can do so such that by today's time, the universe has had enough time for all the matter that was there to come to the same temperature, and the universe to exhibit the large-scale lack of variation that we observe. This weird coincidence that completely opposite regions of the cosmic background radiation have the exact same temperature to a part in 10 to the fourth. And we can do that incredibly accurately. And in this way, this brief amount of time is enough to cause the universe to inflate enough to solve this horizon problem. And we will see how it then impacts on the flatness and on the observation of the universe's lack of magnetic monopoles. So let's take a step back. Imagine a region of the universe. Today we can see that is effectively encapsulated by our cosmic microwave background, these spheres or the surrounding photon shell that comes to us in all directions. So consider the distance to the cosmic microwave background's last scattering surface. That is approximately 40 billion or so light years away from us, even though the universe is only 14 billion years old. It is far larger than 14 billion light years away from us because the universe has expanded so much since that period of time when the CMB was produced, and the universe may have undergone this earlier primal period of expansion called inflation. So the picture that inflation develops is that all the mass and all the energy, all of what would later become the galaxies, stars, and so forth that are contained in the Hubble Deep Field image that I showed at the very beginning, those arose from the same patch of the primordial universe just after inflation. And so what we see today is actually just a different fragment or an expanded version of a very, very extremely uniform region of space-time at an extremely early period of time. And there's not enough time if you just merely extrapolate in the no inflation curve. You can't get to the degree of uniformity that we see in the cosmic microwave background. There's a gap on the far right between the solid line and the dashed line without inflation. And note again that inflation is not needed at a period earlier than about 10 to the minus 36 seconds. So for that reason, people do talk about inflation incorrectly, in my opinion. They talk about it as the origin of time. They talk about it as the origin of the universe. It's really not that. In fact, from the perspective of no inflation versus inflation, they both have a common history before at periods earlier than 10 to the minus 36 seconds, going back as far back as you like, perhaps to the Planck time of 10 to the minus 42 seconds. So that, again, re-emphasizes the point I've made many times on this channel. Inflation is not to be thought of as a theory of the genesis of the universe, but of the evolution of the universe after some period of time, if it indeed is the correct paradigm. And so finally, inflation explains these three problems. It explains the flatness of the universe, solves the problem of the isotropy of the cosmic microwave background, explains why the universe is so flat because it was born exquisitely flat, and it solves the uniformity of the cosmic microwave background, as well as explaining that any region of the universe of any size would have expanded away any magnetic monopoles that were there to far beyond the cosmic horizon. So we might expect only one monopole per universe or per universal sized object. We'll talk about that more later. And so we would never expect to encounter on Earth or in the solar system the magnetic monopole floating around in our observable universe. The odds of that are literally astronomically forbidden. So inflation does all these things. It explains what the universe looks like on its largest scales. We'll see later, where does structure come from? And inflation is a very good theory of cosmic structure formation, provided you accept that inflation actually occurred. Because what inflation will allow us to do is explain not only the large-scale flatness of the universe, but also the small-scale non-flatness and crinkliness of the universe. Namely, how did the universe seed the primordial objects of early wells of dark matter that would then accrete ordinary matter, that would then ignite to form the first stars, galaxies, etc. So inflation has a proposal for that, and for that, I will refer you to our next video. For now, signing off, Brian Keating, Chancellor's Distinguished Professor of Physics and co-director of the Arthur C. Clarke Center for Human Imagination for the Into the Impossible podcast.
If you enjoyed this video, you definitely want to check out this playlist with my cosmology friends talking about the origin and evolution of the universe. And if you're interested in a deep dive in the multiverse, wormholes, and other exotic phenomena, click here and hear my conversation with Juan Maldacena of the Institute for Advanced Study. Enjoy! And don't forget to subscribe for more amazing content.